They say, oh my God, I see the way you shine. Take your hand, my dear, and place them both in mine. You know you stopped me dead while I was passing by. And now I beg to see you dance just one more time. Ooh, I see you every time. And oh my, I like you.
Hello, today we're going to discuss the non-exact differential equations. And before proceeding now to our topic, please don't forget to subscribe to my YouTube channel. Okay, so in our previous lecture, we have discussed the exact differential equations, and we know the standard format, no, or the standard form of the said exact differential equations. And today we are going to discuss these non-exact differential equations, and what are the things that we need to consider if we are dealing with this non-exact differential equation. Okay, so from this standard format of your mdx, previously we have this m as a function of your x or y variable dx, plus we have here this n as a function also of your x or y variable dy is equal now to 0. Okay, and we discussed also that you can use this format, mdx plus this n dy is equal to 0, and this is just the standard form of the differential equation. And since we are discussing now the non-exact, so probably our partial derivative of your m rather, with respect now to your y is not equal now to partial derivative of your n with respect now to x. Okay, and we can say that the given differential equation is not exact. Okay, so how we deal with this one, especially if the given differential equation cannot be solved by variable separable, cannot be solved by homogeneous function, and if we consider the exact differential equation, the given equation cannot be solved also, and we are now here that the given equation is not an exact differential equation. So how we deal that kind of problem? Okay, so for our solution for that, okay, so we need to go into now this solution, especially if we are dealing with a non-exact differential equation. Okay, so we need to have this form of your m. We have now this v dx plus your n times this symbol phi dy is equal now to 0. Okay, such that our partial derivative of m v over this with respect now to y is just equal now to the partial derivative of your n phi with respect now to x. Okay, so we need to have this form m phi dx plus n phi dy is equal to 0. Okay, if we are dealing with a non-exact differential equation, and such that, so we may say that such that, okay, your partial derivative of m phi over this partial derivative of y is equal now to the partial derivative of your n phi over this partial derivative of x. Okay, where where our symbol phi is just equal now to the phi as a function of your x or y variable, and we call this one as our integrating factor. Okay, so this would be then our integrating factor. So what are the special cases of finding this integrating factor? So we may write here the special cases the special cases of finding our integrating factor, phi. Okay, so we have actually case 1, so we have now this case number 1 of finding our integrating factor. Okay, so for case number 1, so we may say when the phi is a function of the integrating factor is a function of x, of your variable x alone. Okay, so take note of this one. Okay, when your integrating factor is a function of the variable x alone, so therefore we can say that we have now this phi is equal now to phi as a function of your x. Okay, and if your 1 over n times this partial derivative of m with respect now to y minus this partial derivative of n with respect to x is equal now to the f function of x. Okay, then we can say that then our phi is just equal now to e raised to the power of the integral of your f function of x dx. Okay, so try to remember this case number 1. So if the phi is a function of x variable alone, so you have this form here, phi is equal now to phi as a function of your x, and then if your 1 over n times this difference of the partial derivative of m with respect to y minus the partial derivative of n with respect to x is equal now to a function of x, then you're going to use this phi, your integrating factor, equal now to e raised to the power of the integral of f function of x dx. Okay, so how about for this another case, so we have here case number 2. Okay, so again, when you may say that it's the opposite of case number 1, when your phi is a function of variable y alone. Okay, so you may say that your phi here is just equal now to the phi as a function of your variable y. Okay, so this is just simply the opposite of case number 1. Okay, and our condition here will be this one. Okay, so let us continue. No, f. Okay, if your 1 over n, okay, times this difference of your partial derivative of n with respect to x minus partial derivative of m with respect now to y is equal now to the f function of y. So we can say that our phi is just equal now to our e raised now to the power of the integral of f function of y, and this is dy. Okay, so this would be now our integrating factor. Okay, and we have now this case number 3, no? So we may write here case number 3. Okay, so what is this case number 3? So when your phi is just equal now to x raised now to the m times y raised now to the n. Okay, this is our case number 3. And if, okay, if your mn over your y is minus, no, minus your nm over x is equal now to the partial derivative, no, of your n with respect to x minus this partial derivative of m with respect to y. Okay, and these are the 3 cases, no, just in case we encounter this non-exact differential equations. So we have to remember this one, no? And if ever this is applicable, so you may use this one of these 3 cases, no, or else you may use all the 3 cases if possible. Okay, so now we are going to proceed to our sample problem. Okay, so we are going to find the solution of the equation x squared plus y squared plus 1 dx plus quantity x squared minus 2xy dy is equal now to 0. So first now we are going to check now if ever the problem did not indicates, no, what method we are going to use here. So if we try to consider, no, if this given equation can be solved using the variable separable, so we may check, no, using variable separable. Okay, and then if you can still remember, no, format for standard form, dy over dx is equal now to f as a function of your x or y variable, and this is just equal now to the j as a function of x times your p as a function of your y. Okay, so if we are going to reduce this one into dy over dx form, so probably we have here, no, we will transpose this one term, and then we will multiply this one with 1 over dx to make it dy over dx, no. So we have here x squared minus 2xy, okay, and this would be dy over dx, okay, is equal now to, so we transpose this one to the other side and multiply by 1 over dx. So this dx will be eliminated now, and this just become equal to negative of your x squared plus y squared plus 1. Okay, okay, so this would be now its form. transporting this one, no? Transposing and transporting this one to the other side, so negative x squared plus y squared plus 1, and then probably our dy, our dx is just simply equal now to the negative of your quantity x squared plus y squared plus 1 over this x squared minus 2xy. Okay, and if we are going to reduce this one, no? So this would probably be equal to negative of your x squared plus y squared plus 1. Okay, over we extract now the x, so we have here x and then x minus 2y. Okay, so this would be then equal now to, okay, so if we are going to separate, no, the x here, okay, so separating the x and referring to this just a function of x, and the y variable referring to now this p as a function of y. So actually we cannot separate, no, because if we are going to, this is x, no, but your second also is having this x minus 2y. So if we are going to itemize this one, so we distribute the negative, no, just for checking. So probably this would be equal to negative x squared over, you have x and then x minus 2y. Okay, and then the second one is minus y squared again, so we have x, no, then x minus 2y, and then we have minus 1, we have here x and then x minus 2y. So our dy, no, over dx will not be in this form, no, of this f function of xy, which is equal now to j as a function of your x times p as a function of your y. So this will not comply, no, with this condition for the variable separable. So this means that the given, no, the given equation, okay, can't be solved, no, the given equation can't be solved by using variable separable. Okay, so we proceed, no, to the second one, no, as we have these previous lectures, no, for the variable separable. How about for the homogeneous? Okay, homogeneous equation or function, no, can we solve this one using the homogeneous function or equation? So we have here x squared plus y squared plus 1, and then dx plus, we have this quantity here, x squared minus 2xy dy is equal to 0. Okay, according to this homogeneous function or equation, that each term must have the same degree. So this term is a second degree, this term is another second degree, but this one is none, no, not a second degree. Okay, this one is second degree, and this one is also second degree, no, because the power of x is 1 and the power of your y is 1. So if you sum up, 1 plus 1 is 2, so that is why it is also a second degree. But this does not comply, no, with this homogeneous criterion of having the same degree in its term. So that is why this cannot be solved, no, hence can't be solved, no, can't be solved using the homogeneous, okay, so excuse me, no, Okay, so can't be solved using the homogeneous function or equation. Okay, so can't be solved using the homogeneous okay function. Okay, so now we are going to proceed if this can be solved, no, using the exact differential equation. So let's try, no, if we can solve this one using the exact differential equation. So for the third, we have here using the exact differential equation, no? So according to this one, that we have to comply this partial derivative f of m, no, with respect now to your y must be equal now to the partial derivative of n with respect now to your x. Okay, so in this case, our m is just m dx, no, so this is dx, so therefore it is our m. Okay, so this is x squared plus y squared plus 1. Okay, and our n is just equal now to x squared minus 2xy. Okay, so if you are going to determine this partial derivative of m, no, with respect to y, in which again, no, I will emphasize that with respect to y, meaning our y is our variable, so any other terms, no, except y is a constant. So here, partial derivative of m with respect now to y, so this is y. Okay, so we have here, so this is 0, so this is 2y. Okay, 2y, and then this is also 0, so therefore we can say that this is 2y. So how about our partial derivative of n, no, with respect to x, where our x here is the variable. Okay, so from here, so this is x, no, x squared, so we can say that this is 2x and 2xy minus our variable is x, so minus 2y. Okay, so we can say that our partial derivative of m, no, with respect to y is not equal to the partial derivative of n, no, of n with respect now to x. So this cannot be solved, no, by using exact differential equation. So we can say that this is not an exact differential equation. Okay, so that is why we have now this topic today, no, this non-exact differential equation. So this is the application, no, of our topic in solving a given equation involving equation that cannot be solved by variable separable, homogeneous function or equation, and this exact differential equation. So we will solve that one using the non-exact differential equation. Okay, so for our case number 1, so if you can remember, no, in our case number 1, okay, so we have there this 1 over n. Okay, and we have this partial derivative, no, of your m with respect now to y minus the partial derivative of n, and this is with respect to x, equal now to the f function of your x. Okay, and substituting now the value of our n here is 1 over this x squared, okay, minus 2xy. Okay, and this is times this partial derivative of m with respect to y, which is equal now to 2y, okay, minus partial derivative of n with respect to x, this quantity, no? So we are going to enclose this one with a bracket, and this is 2x minus 2y, okay. Bracket is equal now to the f as a function of x, okay. And then simplifying, no? So we have here x squared minus 2xy. So we have here 2y minus 2x. So we distribute the negative sign, plus 2y, okay, equal now to f as a function of your x, okay. So this will then be equal now to this one, x squared minus 2xy times the quantity. So we have 4y, no? So 4y minus 2x, okay, equal now to f as a function of x, okay. And then we will extract the 2 here, so this will then be 1 over x squared minus 2xy times we have here 2, okay, and then we have here 2y minus x, okay, equal now to f as a function of your x, okay. So actually we can extract also, no, the x here from this terms, no. So we can extract the x, so we can eliminate, no, this x minus 2y, no? So we will proceed now, okay. So extracting here the x, no. So we have 1 over, we have x times x times we have x minus 2y, okay. Then we will multiply here with 2, and then we have here 2y minus x, okay, equal now to f as a function of your x, okay. And then we have x minus 2y, but here we have 2y minus x, so we are going to extract the negative sign here. So this will then be 1 over x times x minus 2y times 2, and then we extract the negative sign, no? So this will then be x minus 2y, okay, equal now to f as a function of your x. So we can eliminate this one, no? X minus 2y, okay. So we have here 1 over x times we have here, so negative 2, equal now to f as a function of your x. So this will then be negative 2 over x is equal now to f function of x. So this is okay, no? So we can check that this is okay, okay. Case number 1 is okay based on this negative 2 over x is equal now to f as a function of x. So how about if we are going to consider the case number 2, okay. So we will proceed now to case number 2 now, okay. So we will have this case number 2 now. So here case number 2, okay. So we are going to check now. So according to case number 2, our 1 over n times this difference of your partial derivative of your n, no, with respect now to x minus the partial derivative of your m with respect now to y is just equal now to f as a function of your y. Okay, so again, no, working out this equation, so we have here x squared minus 2xy, okay, times, so we have here 2x, no, minus 2y, and then minus this 2y, okay, equal now to f as a function of your y. Okay, so proceeding 1 over x squared minus 2xy times this, we have 2x minus 2y minus 2y, okay, equal now to f as a function of your y, and we have here x squared minus 2xy, and this is times this 2x minus this one, minus 4y, equal now to f function of your y. Okay, so we are going to extract, no, the 2 here, and then we are going also to extract, no, the x here, so we have here 1 over x, and then we have x minus 2y times this quantity, so we have here 2 and then x minus 2y, okay, equal now to f as a function of your y. So we can eliminate this one, oh, okay, and then afterwards we can have now this 1 over x, no, so here we have 1 over x, okay, so 1 over x, okay, times we have times this 2, okay, so times 2 is equal now to f function of your y, or simply this is just 2 over x is not, no, is not f as a function of your y, since we have this variable x. Okay, so we cannot apply, no, this case number 2 actually. Okay, so therefore we can say that those we are going to use, no, case number 1 where, okay, where we have now this f function of x is just equal now to negative, no, 2 over x. Okay, so based on case number 1, we actually have now this integrating factor, no, so here we have phi is equal now to e raised now to the power of the integral of f function of x dx. Okay, so we are going to use, no, this integrating, no, factor phi. Okay, so proceeding now, so we are going to calculate, no, for the integral. Okay, for the integral of our f function of x dx. Okay, so we have here f function of x dx is equal to integral of, we have negative 2 over x dx. Okay, so we will extract the constant, no, So this will be negative 2 integral of dx over x. Okay. So after that, we are going to have this negative 2 times the integral of your dx over x. So by the property of the integral, no? Integral of the u over u is equal to ln u. So we have here ln, our u here is the x, no? So we have ln x plus a constant, no, in which we are going to assign c1. Okay, and then after that we distribute, no? So this will be negative 2 ln x and then minus 2 c1. Okay, so in calculating, no, the integrating factor, this one, no, this constant, we are just going to drop, no, in calculating the integrating factor, no, drop the constant here. Okay, so this will be then equal to the integral of the f function of x dx is then equal now to negative 2 ln of your x. Okay, and then we can further simplify this one, equal now to ln x raised now to negative 2, no, since we have the property of our natural logarithm, no. If you can still remember that the ln x raised to the n is just equal now to n times your ln x. So in this case, we have here ln x raised now to the negative 2. Okay, so after that, we are going to calculate then the integrating factor. Okay, so our phi, which is our integrating factor, is just equal now to e raised now to the integral of f function of x dx, which is then equal now to e raised now to the ln x and raised to the power of negative 2. Okay, so and by property, you know, of the natural logarithm, in which our e raised to the ln x is just equal to x, so we can say that this is just equal also to x raised now to the negative 2. So, okay, our phi, which is our integrating factor, is just equal now to 1 over x squared. Okay, so after this, we are going to use this integrating factor, no, in solving the given non-exact differential equation. Okay, so what we are going to do now is we are going to multiply the given equation, which is yet no non-exact equation. Okay, so we have here, no, from the equation, from the original equation, from the given equation. Okay, so we have here, no, x squared plus y squared plus 1 dx, no, plus here we have x squared minus 2xy dy is equal to 0. So we are going to multiply this one, no, we are going to multiply this one with the integrating factor. Okay, we are going to multiply this one with our phi. Okay, so we have here then this x squared plus y squared plus 1, and then we have dx plus this x squared minus 2xy dy is equal to 0 times our integrating factor of x raised to the negative 2, or this 1 over x squared. Okay, so this distributing this one to this given equation, so we have here x negative 2 times this x squared plus y squared plus 1 dx. Okay, plus we have here this x to the negative 2 of times this x squared minus 2xy dy is equal now to 0, because 0 times this one is just simply equal to 0. Okay, and proceeding, now, so we have here this, you are going to distribute this x to the negative 2, or you may use this 1 over x squared here. So if you are going to distribute, so this would become equal to, so this would be 1 the first term, x squared over x squared is just 1, plus we have the second term is y squared, y squared over x squared, then we have here plus 1 over x squared. Okay, and this is dx, plus the other term is, this would be 1 this one here you distribute, and then this would be negative, we have here 2y over x, dy is equal now to 0. Okay, then after that one, simplify, so we have here this 1 plus, we move up this x squared, so this is x to the negative 2 y to the squared plus this x to the negative 2 dx, plus we have here this 1 minus 2x raised to the negative 1, we move up this x also, times y, and then we have dy is equal now to 0. Okay, so this is the time then that we are going to assign our m, our new m, and our new n, since we already used the integrating factor. So we have here our m, which is this one, so we have 1 plus x to the negative 2 y squared plus x to the negative 2, and we have also our n, which is equal now to 1 minus 2x raised to the negative 1 times y. Okay, so after this we take the partial derivative of m with respect now to y. So take note, y is our variable. Okay, so in this case this is 0, the partial derivative of this with respect to y is 0. This one is, since we have this y, so this would probably equal now to, we have here x negative 2, and then we have 2 times, so we have 2 times y, then 2 minus 1 is 1, so 2y. Okay, 2y, and then here with this would be equal now to 0, since this is being considered as constant. So our partial derivative of m with respect to y is just equal now to 2x raised to the negative 2 times your variable y. So how about our partial derivative of n with respect now to x? So our variable here is x. Okay, so this is 0, and this is our x, so this is, so we have negative 2, and then times the negative 1, and then x, and then x, so we have here our variable is x, so negative 2, and then we have negative 1 times x, negative 1 minus 1, so is negative 2, and then we have this y here. Okay, so simplifying this one, so partial derivative of n, no, with respect to x is just simply equal now to, so negative 1 times negative 2, so this is positive 2, no, and this is x raised to the negative 2 times your y. So take note that our partial derivative of m rather, with respect to y is just equal now to the partial derivative of n with respect to x. So this is already exact. So we can proceed now with our calculation. Since using this integrating factor, we made the non-exact equation into an exact differential equation. So since it is already now an exact equation, so we can proceed using the direct solution. And I will also show you not only the direct solution but also the indirect solution, so that you can compare and verify that those direct solution and indirect solutions are just equal to just arrive to the same answer. Okay, so using now the direct solution of this given differential equation. So first we have now this direct solution. Okay, so we have now this form in solving the given equation using the direct solution. So we have here the integral of your m dx plus the integral of this quantity n minus the partial derivative with respect to y, okay, of your integral of your m dx, okay, quantity dy is just equal now to a constant c. Okay, so considering first now this integral for integral of m dx. Okay, so from here we have this integral of this quantity, no? This is our m. Okay, so this is 1 plus this x negative 2, then we have now this y squared plus our x raised to the negative 2, and then we have now this dx. Okay, so after that one we distribute the integral individually. So in here, since this is dx, our variable is our x, so we consider any other variable except x as a constant. So we can say that distributing this one, this is integral of dx, and then we have here plus, so we will extract the y, so y squared integral of x raised to the negative 2 dx, and then here we have the plus integral of x negative 2 dx. Okay, so this is then equal to the integral of your dx is just now your x, so x plus a constant c1. Okay, so this is for our first term. Okay, for our second term, so we have here y squared, so we will just enclose this one with a bracket now, and this one, the integral of x raised to the negative 2 dx is just simply equal now to, so try to remember your integral property, the integral of your u to the n du is just equal now to the u to the n plus 1 all over n plus 1 plus a constant. So in this case, our u is x and our n is negative 2. So n plus 1 is negative 2 plus 1 is just simply equal to negative 1. So that is why this is just equal to this x to the negative 1 all over 1. Okay, and this is now plus, and this is now plus C2. Okay, quantity, and we enclose this one with a bracket. Okay, plus the third term is this integral, no? So again, we just enclose this one with the bracket, and then this is x minus 1, x raised to the negative 1 over this negative 1 plus our C3. Okay, so after that one, we are going to simplify, no? So we have here here we have this y, no? Y squared. So we have here x, no? So we will separate, no? In the last part all the constant here, and the last part of this calculation. So x, and we have here plus. So this one is x raised to the negative 1 times your y squared, no? This one. And then the third term is plus, no? Plus your this one. Plus your negative of your x, no? Raised to the negative 1. So here in the second term we have x negative 1, no? And then this is actually negative, no? This is negative plus negative of, since this is over negative 1, so negative of x raised to the negative 1 y squared. And then we have here plus c1 plus c2 plus c3. Okay, and simplifying, no, this one, we have now this integral, no, of your mdx is just equal to, we have here x, no, x, and then negative x raised to the negative 1, so this is minus, no? So we have here y squared over x, no? And then since this is we put this down, no, this x raised to the negative 1, and then we have this minus 1 over x, and we will assign, no, plus c4, no, since we are going to assign this c4 equal now to c1 plus c2 plus your c3. Okay, so we are done with this integral of mdx. So for the second term here, so we have this for integral of your n, no, n minus the partial derivative with respect to y of your integral of m dx, okay, dy is equal now to 0. Okay, okay, so we are going to work with this one, no, excuse me, this is not equal to 0, no, this is just dy, integral of your n minus partial derivative of with respect now to y of this integral of m dx. Okay, so working with this equation, so we already knew, no, that we have this integral of m dx which is just equal to this one, no? So this is just equal now to our n is just equal to 1 minus 2x, no, 2x raised to the negative 1 times y, and this is our n. Okay, 1 minus 2 times x raised to the negative 1 times y, no, we have this one, no, in our previous slide, so I hope you also get this one. And then we have this minus, no? Minus this partial derivative, no? With respect to y of this quantity, okay? So what is this quantity? This integral of your m, no? M dx, which is this one, okay? So we have this value, no? Here, okay? So we will just substitute the integral of m dx, no? Which is just equal now to, so we have this x, no? X minus this y squared over x minus this 1 over x plus we have now this c4, okay? And this is here, no? Inside the bracket, and this is integral, no? Integral, and this is dy, okay? And then after we have here this integral of 1 minus 2 x raised to the negative 1 y, okay? So this is quantity minus the partial derivative, no? We go directly to the partial derivative. So here we just remain the minus sign, no? This one, so we just have to distribute the partial derivative with respect to y, no? Which in this case our y is the variable. So we have here so this is 0, no? So 0, and then this one is our y is the variable. So if we are going to have this partial derivative of this y squared, no, with respect to y, is just simply this 1 over x, no? 1 over x, and then we have now this times 2, no? Times 2, and then y raised now to the 2 minus 1 is just to the exponent of 1. So that is why this is just y, okay? And here we have with respect to y, so this is considered as constant, so this is 0, and also this is partial derivative of a constant is 0, and this is dy, okay? And this is equal now to the integral of 1 minus 2 times x to the negative 1 times y, okay? This is quantity, and this is minus, no? Minus here is this negative 2y, okay? Negative 2y over your x, okay? And this is dy, okay? And simplifying, no? So we have here equal to the integral of this quantity 1 minus 2 x raised to the negative 1 times y plus, no? This negative times negative is positive, no? So this is 2y over x, okay? So this is bracket dy, okay? So as you can see, we have some like terms here, no? From this given, from our calculated equation here. So this minus 2 times x raised to the negative 1 times y, no? If we just raise this x, no, up, no? So this is just equivalent to 2x raised to the negative 1 times y. So this will just cancel out, no? So we have then here this equivalent of the integral, no? It's just equal now to the integral of, we have here, so 1 minus 2x raised to the negative 1 times y, and then if we raise up the x there in the third term, so this is 2x negative 1 times your y, okay? So this is dy. So this will just cancel each other out, no? So this is equal now to the integral of your, actually this is just equal now to the integral of your dy. Okay, so let us make this one clear, no? This is just equal now to the integral of 1 dy or integral of your dy. Okay, and the integral of your dy is just simply equal now to y plus a constant, no? Since we already have how many constants here, so we have c4, so we will assign this one as y plus c5. So therefore we can say that the integral, no, thus we can say that your integral of m dx, no, plus the integral of this quantity n minus partial derivative with respect to y of your integral of m dx, no, m dx, and then this is dy is equal now to c is just equal to, this is just equal now to our integral of m dx is simply equal now to this one, no? We have x minus, we have y squared over x, no, y squared over x minus 1 over x plus c4, okay, plus c4, and then the next one, the next term plus the integral of this term here, which is just equal now to this. As you can see, this is just y, no? So this is plus, so we just enclose this one with a bracket, no, to separate, no, the term. So this is plus, the second term is y plus your c5 is equal now to c. Okay, so simplifying, so we have now this equivalent of x minus your y squared, no, over x minus 1 over x, and then we have now this plus y, and then we have now this plus c4, and then plus c5 is equal now to c. Okay, and then we have this, now we will separate now the constants. So we have this one, no, x minus, we have y squared over x minus 1 over x plus y is equal now to, so this is y equal now to c minus c4 minus c5, so which is just equal now to a constant c. Okay, so proceeding, so we have now this final equation, no, actually from this one we have here x, no, x, and then we raise up the x here, so minus x to the negative 1, and then y squared, and then minus, we raise the x here, so x to the negative 1, okay, and then we have plus this y, okay, is just equal now to our final constant c. Okay, so actually this is probably our solution, no, to the given non-exact differential equation. So x minus x raised to the negative 1 times y squared minus x raised to the negative 1 plus c plus y rather is equal now to c. This is our final answer. Okay, So I think that would be it, no, for this day regarding this finding the solution of a given non-exact, no, differential equation. And as what I've told you, no, I want to present to you direct solution. And in this time, no, I've given you the answer given the using the direct solution. And in my next lecture video, I will give you, no, the indirect solution using the indirect solution, arriving at the same answer, no, of this x minus x raised to the negative 1 y squared minus x raised to the negative 1 plus y is equal to c. Okay, so I'll give you that, no, that indirect solution in my next lecture video. So don't forget, no, to subscribe in my YouTube channel so that you can be updated and notified, no, if ever I have a new video, no, in my channel. And thank you very much, no, for listening and watching. And before we end, this will be now our next topic, no, for our next lecture video, the first order linear differential equations. And before proceeding to this one, no, I will just show you the indirect solution of the given nonlinear, no, non-exact rather, non-exact differential equation. And these are my references. And thank you very much once again for watching and listening. And God bless us all and keep safe, everyone.